Hey guys, I'm Jose and this is tutorial number 11 in Rhino Python. And today we're going to see how to, well, it's going to be the second example. So we're going to be working with a curve and we're going to understand ideas of parameters in the curve to find tangents and use vectors with that. So we're going to put together some of the knowledge that we already have, but we're going to just start jumping into some of the methods of Rhino to actually get information out of a curve. So we're going to start by just creating a curve in the canvas. So I'm going to just put 4 points here. Then I'm going to just displace these points vertically, right? Something like that. And what I want to do is basically a curve that has a lot of curvature, right? So I'm going to just push these CVs up and down, so I have something quite, you know, curvy, so we could start seeing some of the work of the tangents in this curve, right? I'm gonna jump into another layer, a red layer, so all the operations that we do with the script um, will result more visible to us, okay? So again, just make anything you want, just a curve, and then we'll be working in a different layer to actually see the result. So what are we gonna do? Basically what we're going to do is just as we've been doing before, we're going to start we're going to say curve. Sorry, let's start from the beginning. Import script syntax as usual. And I want to do something like curve equals directed, right? So we're gonna pick a curve from the string, and we will specify that it needs to be a curve to work, right? Right, so this will be our input for the script to work. And I'm going to do a class. As I said, I'm a big fan of classes, so I want to do everything with classes. So if you haven't seen the tutorials on classes, just go back to that or just follow along this one. So we're going to build a class from scratch. And we're going to say tan lines. This is going to be the name of our class, right? And this class to work, you will need to provide, this will be the constructor of the class, right? A curve, and the number of divisions, right? What we're saying here, these are the two ingredients that you need to provide for this class to work. And so self.curve, this would be like the name, the global variable of the curve, equals underscore curve. You could say str curve and integer number of divisions if you want to specify the kind of values that we're going to use, right? So you could say string, you need to provide a string and an integer, right? Or just do small comments out of that. And I'm gonna put self divisions equals underscore. I'm gonna copy paste that. Oh, that's a little bit of a Java uh, tendency of putting semicolon at the end. Okay, there we go. So we have a constructor for our class, and then we're gonna just define our main function that will be tan points, right? So at this stage, I always like to check uh, if this is working, right? So I'm gonna print check, And going outside the class, I'm going to make an instance of that class, right? And so we're going to say object1 equals timelines curve. So we're going to specify that this element would be the input, and we need to specify as well, like maybe how many number of divisions that we're going to use. And I'm going to specify 50, and then I'm going to say obj1 equals time points, right? So we're going to call this function dot time points. That's it. So at this stage, the only thing we're doing is just calling this function, right? So let's see if we have any errors. Pick a curve. There's one curve. Check. So this is a good way of checking that so far our definition of the class is working. We need to provide two ingredients for the class to work: a curve and the number of divisions. So you could get rid of this check, just maybe bring it up. Okay. Okay. So the next step is just start understanding. We're gonna understand how the curve works. The curve has something called the domain. That is a value. Usually goes from 0 to certain value. It's not necessarily the length of the curve, but it's the description of parameters that go along the curve. So let's get that information from the curve. So domains equals rs dot curve domain. There we go. And we need to specify the curve that we're gonna just calculate the domains, right? So if you press F1, we can go to curve domain, and you can see that the only required value is the ID of a curve we're gonna work with, right? So if you feel like checking that documentation or the examples, that's good. So let's put our curve. In our case, it's called self.curve, right? So it's a curve provided. This is gonna be the DOMS. So let's see what the DOMS is giving us, right? And because let's check that documentation, and DOMS returns a list. And it returns the domain, the upper domain and the lower domain. This is something I know. So we want to print DOMS just to see inside what is the return of that stuff. Like we want to check what's going on inside that. So because we're calling it, let's see right now. Okay, so it's saying DOMS is a list, right? With 0 being the first domain and 39.97, etc., being the upper domain. Again, this is not the length of the line, but it's the parameters. The parameters of each point, any point in the line, it's equivalent to be somewhere between 0 and 39. Right? So we're gonna see how to use that. So we're gonna say something like min domain equals DOMS 0, right? And max domain equals DOMS 1, right? Just because I want to make it simple to me to know that the minimum domain is just the value that is the first value out of that list, and the second one is the maximum domain. So it's the upper limit of the domain. So that's good. And basically what we want to do is use a function that is called rs.curve tangent, right? So let's go and look for that function. So curve tangent requires two things: the idea of the curve and the parameter to evaluate, right? When you start coming across these parameters to evaluate in curves or surfaces, you will understand why this is so important, because we need to understand how to obtain these parameters in order to do operations, right? And it will return a vector, right? So we need to say evaluate, like basically check the curve in some point. How do we specify the point in the curve? With this parameter, and it will return something to us. It will return the tangent. Uh, that's also good. So we could say something like tan equals curve tangent, and we will put the curve as an input, comma. We know that the minimum domain is 0 and the maximum is 39, 30 something, right? So we could say something like max domain divided by 2. So this would be like in the middle of the curve, right? So that's great. We are calling the tangent in the middle of the curve. And then we could do something like rs dot add point in the tangent, right? A vector, that is what we get out of this operation, it's a point, right? So we can actually get the point, draw the point to see it, right? So let's try that. There we go. I'm gonna just minimize this. What are we getting here? We're getting a point somewhere in the screen that basically represents the tangent of this line here. So basically this is not giving us this point, but it's giving us the tangent of that point. Right, so that's kind of confusing, right? So let's do something else. So let's do at the same time pt equals rs dot evaluate curve, right? And if we look for evaluate curve, right? This method requires the curve ID, similar to what we had in tangent, and also a parameter, right? But this one will return us the point, right? So what this function does exactly the same like this one, I mean, requires the same inputs, but instead of returning us the vector of tangent, it will return us the point, right? So let's evaluate those two simultaneously and see what is the difference. I'm going to copy the point and I'm going to draw a point in PT, right? So we're doing two operations, the tangent and the evaluate curve in the same parameter, right? That is the maximum, the upper domain divided by 2. So that should be high. So let's see, right? So if we run that and we see, we have a point created in the center, but we're still getting a point created somewhere here. We need to understand what this means, right? So I'm going to just undo that. And this operation is quite good, but like as we've done before, it's interesting to see like in different instances of the curve, not only in one specific parameter that is the half, right? So I'm gonna just do a for loop out of this. I'm gonna say for I being range from 0 to, that's why we had number of divisions if you were paying attention, right? We're gonna say do all this stuff in a for loop, right? And what is the parameter that we're gonna use? We're gonna say parameter will be, we are gonna pick the maximum domain minus the minimum domain right? So we have, in this case, is we know that minimum is 0, but we are kind of specifying this in case it's not, right? If you trim the curve, if you do anything with the curve, you might change the minimum domain. It will go from, let's say, 14 to 40 or something like that. So we want to have the actual length, the actual domains of the curve, and we are going to divide this by the number of divisions, and then we're going to multiply it by something. So we need something to count with, like we could say I, right? So I is the value that is changing over and over and over again. So this is going to give us like a repetition, like the first time would be 0, the next time would be like the division. Let's say we put 20 here, will give us 1 out of 20, and we're going to keep moving, right? So we can change these domains that we've been using here by our new parameter that it will change every time that we go through the loop, right? So we're going to check this first. Let's see. Right. So let's see what we have. So we have a point every time we evaluate this. We are not getting till the last one, so we need to do some change there. And we're getting all these points here. If you remember, all the stuff that we've been doing with vectors, vectors always relate to the 0, 0 coordinate, so 0, 0 point, the base. So this tangent, what it's giving us, is the tangents relative to the 0, 0. So they're specifying like a little arrow. It's a directionality, but it's not a directionality on top of this element. So we're going to use some vector math to draw some lines and take those points back to evaluate that tangency. So the thing that we need to do here in order to just to get that final point that we were missing, we're going to say +1, right? So we're going to go through the loop just one more extra time, and that would actually solve that problem. So what are we missing? We are missing basically, what if we add these two, tangent and point? So we could say tan point, something like that, is Rhino dot vector add the addition of tangency and point, right? And we could say Rhino rs, right? So add line. So we're gonna use the add line command to create a line between the point that is sitting on the curve and the tan point, right? This, what we're doing here is adding that vector of tangency to the position of the point and then drawing a line between those two to be able to visualize that tangency, right? So let's try to run that. Okay, I'm gonna just cancel this one in order to undo our work, and then we're gonna run it again. Pick the curve, and there we go. Let's evaluate what we got. So we got these little lines that are going from this point somewhere in space to here. So this is showing us that the tangency of this curve at this specific point is aiming in that direction. That is basically taking this vector and placing it where it should be. So this is telling us that the result, that our calculations are going well. That we could see that our tangent evaluation is kind of quite accurate. I'm going to undo this. I would like to say it a little bit more explicit. So for that, I'm going to add a line here saying tangent equals, I'm going to override the tangent by multiplying the tangent with vector math. So vector scale. The vector would be the tangent, and the scale would be 3, let's say. So whatever you are, times 3, right? So let's run this. Let's see. So yeah, now what we're seeing is a much more clear result of the tangent work. Like when it's straight, these lines go kind of along the curve, but when we're starting getting that curvature, we can see that the tangent is much longer. And this is a way of actually understanding basically what is the concept of the parameter of the curve, right? So because a curve is a unidimensional element, we're basically inputting values that are the u values of the curve, and we are getting some information of the curve in that specific point. The interesting thing of doing this as opposed to be doing division, curve division, is that we can actually, this distribution of points doesn't need to be linear, right? Right now we're doing a linear distribution similar to what we were doing before, of like just evaluating, like picking a line and dividing it into a number of segments. But if you want, you can actually make many points here and maybe less points in this area and maybe more here as well to capture, I mean, some some of the curvature or some of the features of the line that you're working with. So at this point you can also get rid of these points that are the tangents, as the tangents are being used for creating the tan point vector. And that's it. As a little exercise I think would be interesting, we'll probably do it in a few more tutorials, is trying to combine this script with the example number 1, basically, where we would draw the lines between two curves, but we would use now not only the point but also the tangent point, and then the tangent point of the other line, and then eventually the point of the other line. So we could actually get these kind of curves between these two lines. So yeah, that's it.